All right, friends, let's do a brief overview of what we learned this whole semester for the exam. Starting in Unit 1, be familiar with the basic hydrology, things of like the water balance, basic water balance for a watershed, how to delineate watersheds, what weather and climate is, especially in Colorado. If you look back at the last two exams, those are going to be some good review for how the final exam might look like, especially some of the content in there. So make sure you know the difference in how extreme weather and just climate occurs across the state. As far as design hydrology goes, be familiar with the different types of approaches for design hydrology, risk-based analysis, know what the probable maximum flood and the probable maximum precipitation are. Also know what the difference between a storm that comes from a 1% AEP rainfall versus a 1% AEP flood event. And be able to take these different kinds of design criteria, maybe it's the 1%, maybe it's the 10%, maybe it's the PMF or PMP, and be able to attach that to a type of infrastructure. You can go back in our lectures to look at what these events are. You can also look at the readings for that. Precipitation, we covered not only the processes, but how we do the precipitation frequency analysis, including Weibull plotting position. Know the difference between a partial duration and annual maximum series. When it comes to design storm synthesis, really, I want you to be familiar with those intensity, duration, frequency curves and how to get information out of them. We're not going to do like alternate block method or temporal distribution. Snow, remember that SWE, snow water equivalent. You know that equation. I'm going to give you guys all the equations you'll need, but just be familiar with how we get the depth of water in snow from the density of snow and the height of the snow. Be familiar with the concepts behind cloud seeding, albedo, and the influence of dust on snow on runoff. Well, we covered evapotranspiration, the Bowen ratio, which is the ratio of sensible heat to latent heat flux. Be familiar with those terms. And how to use this equation to calculate an evaporation rate. Finally, in Unit 2, secondarily in Unit 2, we talked about soil moisture, soil properties, infiltration and interception. So be familiar with those runoff pathways, how infiltration can change over time and how soil properties influence infiltration. For runoff, we had a lot of different pathways, and we looked at how those pathways are influenced by urbanization. We looked at different kinds of infiltration, different kinds of runoff generating mechanisms. So in one case, we had infiltration excess, where the rainfall rate exceeded the infiltration rate of the soil. And that can change over time. We also have saturation excess, which is when the water table rises from below and creates saturated conditions from below. Know how to do the curve number method and know what you're doing here, right? We're using the curve number method to estimate the runoff depth, which can be converted to a volume when multiplied by an area. We have antecedent soil moisture conditions that can influence the curve number. As far as watershed hydrology goes, in the exam, we looked at different kinds of watersheds and how that influences the runoff hydrograph. Know how water flows through a network, how drainage density and network pattern can influence the runoff characteristics of a watershed. Know the components of a hydrograph and how different kinds of watershed characteristics can influence the timing and shape of a runoff hydrograph. And then time of concentration. What is it? How do we calculate it, right? It's got those three components. Be familiar with, say I give you a problem that has, and I ask you to calculate time of concentration, be able to use these equations to calculate the time of concentration by adding up those components. As far as the unit hydrograph goes, we dealt with that a lot in the last exam. The triangular unit hydrograph, know the equations that we use in terms of the base time, the time to peak, as well as the peak discharge. Those are important components of the unit hydrograph, the triangular unit hydrograph that we used. And then once you create that unit hydrograph, it's usually going to have units of CFS per inch, we want to be able to scale that based on an input rainfall event, right? That has a certain depth in inches. You multiply that depth by the hydrograph Y values, the unit hydrograph Y values, and then you get CFS. From a qualitative standpoint, be familiar with hydrograph routing, how it works, what celerity is, what peak attenuation is, and be familiar with the different methods from hydrologic to hydraulic methods. We talked a lot about kinematic routing, which is a simplified way to do it from a hydraulic standpoint. As far as statistical hydrology goes, there's a lot in here. For me, understanding the concepts of statistical hydrology. So go back and look at what non-stationarity means, what influences that, understand how to compare two different kinds of rivers with different kinds of runoff generating mechanisms and flood magnitude and frequency. So the homework for this would be a really good reference. When in the first part we compare the two different kind of runoff series, and be sure you know how to summarize them, at least qualitatively. I'm not going to have you calculate a standard deviation, right? But know what coefficient of variation is, how that's different from variance and standard deviation, and know what those types of metrics tell you. So if I give you two different kinds of streams and I want you to compare them based on their climate, then I want you to be able to tell me some of the statistical properties of those streams based on what you know about how mean, variance, and coefficient of variation change. Be able to interpret flow duration curves as well as those log Pearson distributions for flood frequency analysis. We have regional analysis, right, which is what StreamStats does. It does regression equations based on regional data. You know what mixed populations means, how we can have snowmelt floods and rainfall floods in the same river, and they have two different populations associated with them. And then as far as the last unit goes, we started off with floodplain management. So be familiar with different aspects of floodplain management that we talked about and learned about in the homework. So it's mapping, communicating risks, be able to interpret floodplain maps, and know how they're generated through HEC-RAS modeling. What kind of data do we need? Model boundary conditions. Understand the difference between 1 and 2D models, as well as steady and unsteady flow. So 1D models, I'll just briefly summarize, work well when you have a channel that's very well defined. The flood is going to typically be confined to the channel or a relatively narrow corridor of the floodplain. 2D models are important when we have flow that's splitting or flow that's going out and distributing, as opposed to flow that's like confined to a valley and moving in just one direction downstream. That's when 2D models are important. That could be something like an alluvial fan, that could be something like a levee break, or a distributary channel that maybe has either side channels or the flow is spreading out over a wider area and not just focusing downstream. And then groundwater. So we did 3 lectures on groundwater. The first one covered a lot of these concepts related to permeability, conductivity. This was the important one, which is the property of the aquifer and the fluid. Know the difference between a confined and unconfined aquifer, as well as the potentiometric surface. What is that? How does that differ between a confined and an unconfined aquifer? As far as steady groundwater hydraulics goes, what does it mean to have steady state conditions for a groundwater problem? Understand Darcy's law, what that means. Remember, it's a function of the hydraulic conductivity and their gradient. The cone of depression problems that we did, so that was calculating either hydraulic conductivity from a well that's being pumped at a certain discharge, and we know some water level measurements at steady state, right? This has been happening a long time. The water levels aren't changing over time. We could also calculate the discharge from known hydraulic conductivity and water level measurements. Finally, we could right, those are the two problems that we could have. We could also say, I want to pump out this much water and I know the hydraulic conductivity, how far is the water level going to drop? So for these kinds of problems, it's really important to remember what the input variables are. And if I give you a word problem, you're going to need to be able to calculate the input variables. They're not going to be handed to you directly. So what does H actually mean? What does R actually mean in these equations? We talked about unsteady groundwater hydraulics, so be familiar with the concepts, but we didn't do any problems for these. Those are the topics that we covered for the class. That's in a very quick nutshell. As far as the exams go, oh yeah, we also did urban hydrology, that example in class. So certainly be familiar with that. We didn't do a homework on it, so just keep that in mind. But understanding the concepts of urban hydrology calculations, or maybe we have a problem where we use some of the runoff calculations that we did in terms of the peak discharge, either from the hydrograph method or the rational method, and as well as time of concentration. So be familiar with those kinds of things. I'd say the best way to study would be to certainly look back at the old exams that we've already done in class for this semester. Be familiar with how to do those problems, and make sure you do your crib sheets. So you can bring the previous 2 crib sheets that you already made, or you can make 3 new ones, but you can have up to 3 pages. You can make a new crib sheet for this last unit. I'll be available for office hours on Monday. I'll send that out in an announcement or an email, so take a look for that.